Thank you. Thank you. Thank you. Thank you.
You're being uncharacteristic.
Computer scientists and philosophers of antiquity, they speak a lot during, sorry, it's just a joke. Okay, so that's a pleasure. This is, by the way, what's important to notice, that is the last section of the year, because next seminar is cancelled, because Pino Strangi, that should have given the talk, have a family problem, so will not be able to come. So he will probably come in the springs now. So we have only two choices to cancel. If someone of you want to give a talk, we can replace. But I think that the students in particular already a lot of seminar. So also if we make 1 week free is not terrible, except if they pretend to have a supplementary talk. In this case, I give again a call for a very, very, very hard technical matter that then you have to write on in a very detailed way. Okay, so I think that we are unanimous in considering that the next talk is cancelled. So this is the last talk of the term. We begin again on January 12th with a whole day that we organized in occasion of the Day of Logic. You know that the Day of Logic is January 14, and it's January 14 because it is the date of the birth of Gödel. And so this is the reason for which any year the UNESCO as a day, and so we decided to participate to this international event that is to do something, the Day of Logic. But insofar as the Day of Logic this year is Sunday, normally there are events in the Friday or the Monday. So, and then we have one on the Friday. Okay, I think that the program circulated already, and so you are all invited, especially the students, to come for this event. Now it's a pleasure to have together with us our colleague Emily Adlam from Chapman University. It's 3 months that you are in Chapman.
Yeah, that's right.
So that's possibly also an occasion to welcome Emily. I think that you have been already welcomed by other colleagues, but in this official sense, welcome in Chapman and welcome in MPP. Okay, what does non-absoluteness of observed event mean with non in parentheses?
Yeah.
The usual custom here is to have interruptions for clarificatory questions,
Sure.
and then a discussion in the end, if you agree.
Sounds great.
Perfect. So it's to you.
Great. Well, hi, everyone. Thank you very much for coming. I appreciate you being here when you could be at happy hour. So what I would like to talk about today is this issue of absoluteness or non-absoluteness of observed events, which has become a topic of great interest in quantum foundations recently. There have been several theorems proved related to this topic, and people have been using them to argue that quantum mechanics, in some sense, is demonstrating that observed events are not absolute. So I'm personally skeptical that these theorems demonstrate in any strong sense that observed events are not absolute. And so what I want to do in this talk is first give a sort of brief non-technical introduction to these theorems, and then try to understand what exactly non-absoluteness is supposed to mean in this context and what conclusion we should draw from them. So I'm going to begin by introducing the theorems, and then I'll sort of briefly survey the landscape of possible responses to them. And then in particular, I'll focus on the possibility of rejecting the assumption of absoluteness of observed events and try to understand what that means in concrete terms. And I'll argue that what it means in concrete terms is the acceptance of some kind of disaccord. So I'll talk about two different kinds of disaccord that come up in various non-absoluteness theorems. And I'll argue that neither of these kinds of disaccord really indicates that the non-absolute absoluteness of observed events in a strong metaphysically radical sense. I'll then argue that furthermore, considerations related to intersubjectivity mean we probably can't accept at least type 3 disaccord, and so we'll have to respond to these theorems in another way. And finally, I'll argue that retrocausality might be a more viable way of responding to these theorems. So quantum mechanics is a theory which has been around for more than 100 years now. It's a very successful theory empirically. It's led to a bunch of amazing technological developments, but there are still a lot of problems around the issue of how it should be interpreted and how we should understand it. And so in particular, many of those issues relate to questions around measurement, and there's a sort of a collection of different problems related to measurement that we can loosely call the measurement problem. So one way to bring out what some of those problems look like is to consider a situation known as the Wigner's friend scenario. So in this scenario, basically, we imagine putting one of our friends in a box, and we give the friend a quantum system, and the friend is going to perform a measurement on that quantum system. So presumably the friend, when he performs the measurement, sees a definite outcome to his measurement. That's what we expect to happen during a measurement. But if you, from the outside, try to describe this whole scenario quantum mechanically, what the mathematics says is that your friend and the system end up in an entangled state, which looks like a superposition of all the possible outcomes. So mathematically, it looks like the friend is in some kind of indefinite state that combines all the possible outcomes for the measurement. So naively, it looks like there's some kind of contradiction here. The friend presumably must have experienced a definite outcome, but we don't see that in the mathematics. What we see in the mathematics is this mixture of all the outcomes. So already here we see some kind of problem emerging, but we can sharpen that problem by considering more specific scenarios, as is done in various extended Wigner's friend scenarios. So in the case I'll consider today, this involves having two friends, putting them inside separate boxes and giving each of them half of an entangled pair. So we'll then allow our friends inside the boxes to each perform a measurement on their particle, and then finally we'll perform measurements from the outside on the whole box friend particle system. So we'll end up with 4 measurement outcomes, 2 made within the boxes and 2 made from the outside on the whole box system. And furthermore, we'll usually consider a scenario where we're allowed to choose between 2 possibilities for what measurement to perform on the outside. Possibility 1 is just to open the box and ask your friend what outcome they obtained. That is a form of measurement. The other possibility is to maintain complete coherent control over the system and therefore instead perform a quantum measurement in a basis which does not commute with the variables that store your friend's memories. So in practice, what that means is that that measurement will end up erasing the memories that your friend has of the outcome they observed. So there are 2 options for each of those external measurements, either just talk to your friend or perform this complex quantum measurement. So in the theorem of Bong et al., they consider this setting and they imagine what it might look like to give a physical account of what is going on in this series of measurements. So in particular, they imagine 3 properties that we might naturally expect a physical account of the situation to have. So you might expect that such an account should be local. You might expect that it should obey no superdeterminism, and you might expect that it should obey absoluteness of observed events. But what they show in this theorem is that any physical account which obeys all 3 of these assumptions will necessarily produce predictions which are not compatible with the predictions of unitary quantum mechanics as applied to that whole experiment outside of the box. So this is not an experiment we can actually do right now. It's very likely an experiment we will never be able to do, but nonetheless we can calculate what quantum mechanics says would occur if we could do this experiment. And if quantum mechanics is right about that, it looks like we're going to have to give up at least one of these assumptions. So to be more specific about what these assumptions say, the first one is a locality assumption, which loosely speaking is just insisting that there should be no action at a distance. So if I perform a measurement at one point in space, my choice of measurement can't instantaneously influence outcomes obtained elsewhere in space at a similar time. The second one is no superdeterminism, which simply requires that the outcome of the measurement that's performed inside the box can't depend on the choices made later on about which measurement we're going to perform on the whole box system. So that is, the measurement outcome inside the box doesn't depend on whether I later ask my friend about that outcome or erase it using a super measurement. And finally, we have the absoluteness of observed events. So roughly speaking, this assumption is meant to mean something like observed events, so measurement outcomes, are unique events which are not relativized to anyone and anyone or anything, so they are definite in some kind of objective third-person sense. But what exactly this means in this particular context is a little bit unclear. So one of the things I want to do in this talk is unpack in more detail what this assumption of absoluteness of observed events actually needs to be to prove these theorems, and thus what we can conclude from rejecting it. So the question is, how are we going to respond to these theorems? So we have a variety of different options because these experiments haven't been performed, and so we don't actually know what the results of them would be. One viable option is just to say, well, perhaps these experiments would not in fact have the outcome predicted by quantum mechanics. Perhaps they would have some other outcome. And if the outcomes are not as predicted by quantum mechanics, the contradiction on the previous slide can't be derived. And there are indeed various proposed interpretations of quantum mechanics which would indeed predict that these experiments would have a different result from the one predicted by standard quantum mechanics. So in particular, any interpretation of quantum mechanics which predicts something like a wave function collapse when the first particle is measured will necessarily predict something different from standard quantum mechanics for the external measurements performed on the outside of the boxes. And so if you adopt that kind of interpretation, you have immediately solved this problem. The predictions that lead to the contradiction will just not come true. But there are some technical reasons to think that maybe it's a bad idea to deny the universality of quantum mechanics in this way. It makes things very difficult when we try to accommodate more complex physical scenarios. And so while this is still a possible option, there are certainly good reasons to think it would be nice if we could figure out how to accommodate the predictions of standard quantum mechanics. So for most of the rest of this talk, I'm going to just assume that if we could perform this measurement, it would in fact have the results predicted by standard unitary quantum mechanics, and I'll try to understand how we could respond to that if that were in fact the outcome. So if that were the outcome, it seems as though we're going to have to reject one of the three assumptions that goes into proving this theorem. So one option is to reject either locality or no superdeterminism. That in fact is my preferred option, and I will talk about that later. But what I want to start by examining the possibility of rejecting absoluteness of observed events, because that's the possibility that people have been getting excited about and have been using to argue for various radical possibilities. So absoluteness of observed events is this idea that measurement outcomes are unique, non-relative events. Measurements have just one outcome, which is shared by everybody. So there are a number of different ways in which you could envision rejecting this assumption of absoluteness of observed events. And one fairly straightforward way to do that is just to say, well, actually measurements have more than one outcome. So in particular, that's the kind of thing we see in a many world style interpretation. So an interpretation which says that when a measurement is performed, the person performing that observation branches into a number of copies, and each one of those copies sees a different outcome. So that kind of branching picture immediately avoids the contradiction from the previous slide, and it seems reasonable to say that indeed, in a sense, observed events are not absolute in that picture, since observed measurement outcomes happen in a variety of different ways in different branches. However, the people who have been interested in these theorems have mostly been using them to argue not just for the many worlds interpretation, but for some other kind of non-absoluteness of observed events. So what I want to focus on here is trying to understand what this other kind of non-absoluteness might look like, and whether it really is a viable route. So in particular, the style of approach people have been interested in involves saying something like, when a measurement is performed, that measurement has only one outcome for each observer. So any given observer will have a conscious experience of exactly one outcome. But nonetheless, observed events are not absolute because measurements can have different outcomes relative to different observers. So this event, there's a definite outcome relative to me, but there may be some other definite outcome relative to you, and thus, in that sense, observed events are not absolute. And these kinds of relational or perspectival ways of thinking about quantum mechanics have been used to motivate a variety of quite strong claims. So I've seen people using these approaches to argue that quantum mechanics shows us that there is no objective reality, or that all physical facts must be relativized to an observer, or that facts are subjective, or that it is not even meaningful to make comparisons between the perspectives of other different observers. And so these are strong claims. One needs a strong argument for strong claims. So what I want to do now is try to understand whether these theorems really do provide any kind of compelling argument for these kinds of claims, or whether this is being taken a little bit too far. So specifically, we'll be considering what are known as relational or perspectival interpretations. So that is, again, interpretations which say that there is one outcome per measurement per observer, but measurements can have different outcomes relative to different observers. So different observers can disagree about the outcome of a given measurement. And moreover, when they disagree, it's not because one of them is right and the other one is wrong. It's really supposed to be because there are just different facts for both of them. There's no sort of third person objective reality. Each person has their own reality. So an immediate question you might have about this kind of picture is that it sounds a bit weird to say that a given measurement can have different outcomes relative to different observers. So in particular, all of these views agree that there is one observer who performs the measurement, and the person who performs the measurement sees one particular outcome. And so you might think that even if other observers think there was some other outcome, surely the person who actually performed the measurement is in some sense privileged. Wouldn't it be reasonable to say that the outcome observed by the person who actually performed the measurement is the uniquely correct outcome, and anybody else who thinks there's a different outcome is just in some sense making a mistake? So in order to understand what it's supposed to mean to say that a measurement can have different outcomes relative to different observers, I think it's helpful to look at a little bit more detail about how this works in the context of these actual theorems. So having gone through a number of these theorems, I found at least 3 different ways in which these theorems demonstrate the possibility of disagreement between observers about measurement outcomes. So I call these type 1, type 2, and type 3 disaccord. I'm not going to have time to talk about type 1 disaccord in this talk, so I'm just going to skip to type 2 and type 3. So first of all, type 2 disaccord involves the possibility where we have one observer, Alice, performing measurements on another observer, Chidi, and the idea is that there is some quantum state, psi, which seems like the correct state for Alice to assign to Chidi. So it's correct in the sense that it gives all the right predictions for the outcomes of all of the measurements that Alice could possibly perform on Chidi.
It's possible that it's not Bob. It's Chidi. That's quite strange. What is that?
So this is taken from an extended Wigner's friend experiment in which there's 4 observers. Oh, so there's also a Bob involved, but he's doing something else. So yes, Alice is performing Chidi, and Bob is elsewhere measuring a 4th observer. Yeah, Alice is measuring Chidi. She observes outcomes which are consistent with Chidi being in the quantum state psi. And furthermore, the quantum state psi is naturally interpreted as representing something about Chidi's experiences. So we have type 2 disaccord if whatever this quantum state seems to be representing about Chidi's experiences doesn't agree with what Chidi is actually experiencing. So this is the kind of type of disaccord that we get in the Wigner's friend scenario. As we saw then, what happens is that we have our internal observer, and our internal observer has observed a definite measurement outcome, but for our external observer, the correct state to assign to that observer, the state which correctly describes the outcomes of all the measurements that they could make, is a state which represents the observer, the internal observer, as being in a superposition of all the outcomes. So the natural way of interpreting that state seems to be to say that Chidi, the internal observer, is in some kind of indefinite mixture of all the outcomes. But as a matter of fact, Chidi has experienced a definite outcome. So we have disaccord in the sense that what Alice would naturally conclude about Chidi's experiences based on the state that she finds when she measures him is not a good reflection of what Chidi is actually experiencing. So what the Wigner's friend scenario in its original form seems to demonstrate is primarily the existence of type 2 disaccord. And so the question is, does the existence of type 2 disaccord need to lead us towards postulating some kind of radical relational or perspectival view, or towards thinking that there's actually no objective reality. And I think sort of naively, the answer is no, because we certainly have the option of just saying that what's going on here is that Alice is just making an incorrect interpretative assumption. Alice is observing that Chidi appears to be in a certain state from her point of view, and then she is drawing some conclusion about what that state means for Chidi's internal experiences. But that is a non-trivial interpretative assumption that she doesn't have to make. She could simply refrain from making that assumption, and then we would no longer have this apparent clash between the beliefs of Alice and the beliefs of Chidi. So the view that this kind of disaccord does involve some kind of strong relationalism or perspectivalism seems to come from conflating two different meanings of the word state. So we tend to use the word state in quite ambiguous ways throughout physics, meaning a number of different things. It's helpful here to disambiguate two particular notions. So state can refer to something like the intrinsic condition of a system, so an intrinsic description of a system at a given time. So in particular, one might naturally expect that a system's intrinsic condition at a time is responsible for its conscious experiences if it is a conscious system. So in this experiment we've just described, we might naturally expect that Chidi's intrinsic condition is what determines his experience. We can also think of states in terms of what I call the interaction state. So in this sense, the state is a mathematical object encoding predictions for the outcomes of measurements performed on the system. So the interaction state in the scenario I've just described is the state psi. That state is a correct description of all the predictions for Alice's measurements on Chidi. It's a description of the interaction between Alice and Chidi. It's not in and of itself a description of Chidi. So the idea that the existence of type 2 disaccord needs to lead us to some kind of radical perspectival picture seems to come from assuming that the intrinsic condition has to be the same as the interaction state, or that there has to be some quite specific mapping between them. Because if we identify the interaction state with the intrinsic condition, then indeed it seems as though if Alice finds Chidi to have an interaction state psi relative to her, she's obliged to conclude that his intrinsic condition is being in an indefinite mixture of all possible outcomes, whereas we know that from Chidi's point of view, his intrinsic condition is that he has seen a specific outcome, and so it seems as though there's just no fact of the matter about Chidi's intrinsic condition, and so we have to go to some kind of radical perspectival picture. But if we don't insist that intrinsic conditions have to be the same as interaction states at all times, then we're not forced to do that. We can simply say that in this particular kind of situation, the interaction state as seen by Alice is not a good reflection of the intrinsic condition that Chidi is actually in at that time. And so in particular, there's a good reason to separate intrinsic conditions from interaction states. And that's because intrinsic conditions are sort of naturally thought of as being properties of systems in and of themselves, so not being relational. But interaction states seem as though they could very well be relational. That's because an interaction state is all about the outcomes that will be seen in an interaction between a system and another system which is measuring it. So it seems not unreasonable that the interaction state should depend not just on the properties of the system, but also on the properties of the person performing the measurement. In general, we do expect that interactions depend on both systems involved and not just on the one system. So it would be quite reasonable to say that interaction states should indeed be relativized to the observer, and that therefore different observers could assign different interaction states to the same system because they are going to have different interactions if they try to measure it. So that provides a good reason to think that intrinsic conditions are not always going to be the same as interaction states. And it also provides a natural way of understanding what's happening in the Wigner's-Friend scenario, where we can simply say, Chidi has a single well-defined intrinsic state all along. His intrinsic condition is that he has seen a definite measurement outcome, but the interaction state of Chidi relative to Alice is not the same as the interaction state that Chidi would naturally assign to himself, or the interaction state that he would assign to the system that he's measured. And so we have relativized interaction states, but absolute intrinsic conditions, and we can therefore explain what's going on in the Wigner's-Friend scenario without having to postulate, without having to lose objective reality or anything like that. So in conclusion, it seems to me that although the Wigner's-Friend scenario does indicate the existence of type 2 disaccord, and that is very interesting and important, it doesn't necessarily provide any strong reason to go down this radically perspectival route. So the second kind of disaccord that I'm going to talk about is type 3 disaccord. So this one is what occurs in the Bong et al. Theorem. So type 3 disaccord involves a situation in which Chidi performs some measurement, and then Ellis comes along and asks Chidi what the result of his measurement was. And we have type 3 disaccord if it's the case that what Ellis hears Chidi saying in this interaction may not agree with what Chidi himself experienced the result of the measurement to be. So this is the kind of disaccord that occurs in the Bong et al. Scenario. And to see that, it's helpful to note that the absoluteness of observed events assumption that's used to prove this theorem can actually be broken down into two parts. The first part is just the assumption that I call AOE1, which requires that measurements have only one outcome per observer. So AOE1, roughly speaking, is just ruling out the many worlds interpretation and other things of that kind. AOE2, meanwhile, is an assumption about communication between observers. AOE2 is assuming that in the case where Alice chooses to make the measurement where she just opens the box and asks Chidi what his outcome is, in that case, what she hears will generally match what he actually saw. So AOE2 is just assuming that we don't get type 3 disaccord in this situation. So these two assumptions together are sufficient to derive all the conclusions that Bong et al. Derive from their absoluteness of observed events assumption. And so that means that anyone who advocates responding to the Bong et al. Theorem by rejecting absoluteness of observed events must ultimately be rejecting one of these two assumptions. So rejecting AOE1, of course, leads to a multiple outcome per observer view, such as the many worlds interpretation. And therefore, anyone who is suggesting that there's some alternative to the many worlds interpretation in this vicinity ultimately has to be rejecting AOE2 and thus postulating the existence of type 3 disaccord. So in the context of the Bong et al. Experiment, postulating the failure of absoluteness of observed events seems in the end to come down to either advocating for a many world style view or advocating the existence of type 3 disaccord. Yes.
Just a clarificatory question. So if you take the type 2 disaccord route,
yes,
are you not really denying absoluteness of observed events and then you have to deny one of the other assumptions, or are you still denying absoluteness of observed events?
Yes. So if you accept the existence of type 3 disaccord,
type 2.
Type 2. Type 2 is not enough to explain the Bong et al. Scenario because it depends on it also depends on the outcome of this particular interaction. So rejecting AOE2 leads to type 2 disaccord, and so it seems that ultimately what it comes down to reject absoluteness of observed events here is either to advocate for a many world style approach or to argue that we should accept type 3 disaccord in this situation. So again, the question then is, if we decide to accept the existence of type 3 disaccord, does that push us towards having a radically relational perspectival approach? Does that mean that we have to say there is no objective reality? And again, it doesn't seem to me that that's the case. The idea that Ellis and Chidi could have an interaction in which Chidi says something and Ellis hears something different is certainly weird, but it doesn't seem incompatible with the existence of absolute objective facts. You can make this work within a perfectly well-defined objective reality just by defining some kind of funny dynamics such that the dynamical interaction between Ellis and Chidi is restricted in certain ways, and in particular, that interaction is not capable of transferring information between them in the way we would normally expect. So while the existence of type 3 disaccord would certainly be very surprising and unusual, it doesn't in and of itself seem to require any kind of strong relationalism or perspectivalism. It certainly doesn't seem to entail immediately that there are no objective facts. So it seems to me that there's no particular reason to interpret type 3 disaccord as indicating that there is no objective reality unless you are already in some sense predisposed towards that kind of view. So again, it's not clear to me that rejecting absoluteness of observed events in this theorem really provides any sensible route to arguing for radical relational or perspectival views, or for thinking that there is no objective reality. If what you want to do in response to this theorem is accept the existence of type 3 disaccord, that's a valid response, but that doesn't in and of itself mean that any of these more radical possibilities need to hold. So with that said, I also don't think that accepting the existence of type 3 disaccord can possibly be the right way to respond to this theorem. So to see that, let's just sort of take a step back and think about type 2 and type 3 disaccord and the extent to which they are acceptable as components of a scientific worldview. So type 2 disaccord, broadly speaking, seems like something we can possibly accommodate. That's because, as we sort of saw, type 2 disaccord essentially comes down to a problematic interpretative assumption. Type 2 disaccord arises from one observer making observations that suggest to them that some other observer is in some interaction state, and then just assuming that means something about the experiences of the other observer, which it does not in fact mean. So as long as we properly understand the existence of type 2 disaccord and incorporate that into our assumptions, we can just avoid this kind of disaccord by making the right assumptions. Type 3 disaccord, on the other hand, seems much more dramatic and problematic because the point of type 3 disaccord is that even in completely ordinary conversations between two observers who are just trying to exchange information about their observations, they're not going to be able to exchange information. They're not going to be able to reliably share information about what they have observed in their separate experiments. And that seems like a very serious problem because so much of scientific practice relies on observers sharing their observations. None of us has the resources to completely confirm quantum mechanics or any other scientific theory on our own. When we do empirical confirmation, we necessarily have to rely on the efforts of many other observers all across the world and the things that they report to us about their observations. So it seems that in order to make sense of science and of the practice of empirical confirmation, we have to have an assumption in place that when we communicate with other observers, by and large, we succeed in exchanging information and we're really able to learn about what they have experienced. So for that reason, it seems like we just can't reasonably accept that in perfectly ordinary interactions, like two observers having a conversation about their measurement results, those observers will generically fail to communicate anything. We have to assume that communication is by and large possible. So for that reason, it seems that accepting the existence of type 3 disaccord in this situation just is not a viable way of interpreting this theorem. That if we choose to interpret the theorem that way, what that will mean is that we'll no longer be able to rely on the empirical evidence that we have for quantum mechanics, and therefore we will no longer have a good reason to believe in quantum mechanics at all. And it doesn't make sense to interpret quantum mechanics in such a way that it undermines the reasons we had for believing in quantum mechanics in the first place.
It's a proof by absurd.
Yes, yeah, it's a self-undermining view. So I think it seems to me that accepting type 3 disaccord is just not a viable option. We can't do that if we are to make any sense of scientific epistemology. So of course, the wrong at all theorem tells us that we can't avoid type 3 disaccord if we keep all the other assumptions. And so that tells us that since we can't reject type 3 disaccord, we are going to have to reject one of the other assumptions. So basically that means either we reject locality or no superdeterminism, or we accept some kind of mini-world style approach, or we accept that quantum mechanics is not universal and therefore this experiment would not have the results that unitary quantum mechanics predicts. So for various reasons, also related to epistemology, I think that many-world style approaches are also problematic. And as I've noted, there are various technical reasons to be worried about the approach of denying the universality of quantum mechanics. So my somewhat tentative conclusion is that the right way to respond to these theorems is probably to reject either locality or no superdeterminism. In fact, I think probably both of these assumptions should be rejected, but I'm going to focus on the no superdeterminism one here because I think the way in which this works in this particular context is quite interesting and tells us something more generally about effects like these in quantum mechanics. So specifically, the no superdeterminism assumption is the assumption which says that the outcome of the measurement performed inside the box can't depend on the choices made later on about which measurement to perform. So one way to reject that assumption is to postulate something called superdeterminism, which I won't talk about in detail here. The other way to reject this assumption is to postulate retrocausality. So to say that there's some kind of causal influence from the choice made later on to the earlier outcome. So people are often very wary of accepting models with retrocausality, and I think they're wary for good reasons. There are some obvious problems that arise in generally in retrocausal models, and in particular, and one kind of problem that very often occurs in retrocausal models is logical paradoxes such as the grandfather paradox. So the grandfather paradox is a thought experiment initially from the philosophy of time travel. It imagines a time traveler going back in time and killing her own grandfather before he can father any children, in which case, of course, the time traveler will not be born. But then if she's not born, she can't go back in time and kill her grandfather. So it seems as if there's no logically consistent way of resolving this cyclic set of events. So we can easily imagine constructing a similar kind of paradox in the context of a retrocausal theory. Our enterprising traveler can just stop using a time machine and instead use some kind of retrocausal influence to cause her grandfather to die before he can father any children. And more generally, in any retrocausal theory, there's going to be a danger of logical paradoxes whenever we have some kind of cyclic structure. So any time where we have an event A in the future, which has a retrocausal influence on an event B in the past, but also the event B in the past has a causal influence on event A in the future, that cyclic structure is likely to give rise to paradoxes of this kind if we make the right kinds of choices. So those kinds of cyclic structures are one of the big problems with retrocausality and one of the reasons why people are not very willing to accept that as a possibility. So the interesting thing about the possibility of retrocausality in the Bong et al. Theorem is that this is precisely the kind of situation in which those cyclic structures cannot occur. And the reason for that is that what Alice is doing is that in order to use retrocausality to avoid the problem here, what we would have to do is say that the outcome inside the box depends on Alice's later choice about whether she is going to open the box and ask about the outcome, or whether she is instead going to perform a measurement which involves maintaining complete coherent control over everything and erasing the measurement outcome. And the key thing to know about that second type of measurement is that it's impossible to do that kind of measurement if any information escapes from the box. So what it means for Alice to maintain complete coherent control is that all of the information about the outcome of the measurement has to remain inside the box and can't escape and get to Alice. So that means that if Alice knows anything about the outcome that was obtained inside the box, she can't choose to perform that second measurement. Her only option at that point is to open the box and ask Chidi about what he observed. And therefore, in any situation where Alice does still have a choice about which measurement to perform, it must be the case that she doesn't know anything about what's happened inside the box, or equivalently, no information has escaped, and therefore there's no causal influence from the outcome inside the box to Alice's choice. So that means it's impossible to set up this kind of cyclic structure in this case, because although we have a case in which the outcome potentially depends on Alice's later choice, it can't be the case that Alice's later choice also depends causally on the outcome, because if she has a choice, then there can't be a causal dependence. So in this case, we do have a retrocausal influence from our future event to our past event, but there cannot also be a causal influence from the past event to the future event. So we can't set up this kind of cyclic structure, and so we can't get the kinds of logical paradoxes that make people worried about retrocausality. And so this I think is interesting. It's not sort of conclusive, but the fact that the retrocausality we would need to avoid the problem here is precisely the kind of retrocausality that isn't vulnerable to one of the major criticisms of retrocausality. Seems to me some indication that perhaps retrocausality might actually be the right way to go here, because it's such a striking fact that it's the special kind of retrocausality that doesn't lead to problems. So more work is needed to establish what a retrocausal model would look like specifically in this context. But based on this fact about the retrocausality required, that seems to me like possibly the most interesting kind of path to pursue here. So just to conclude, I do think that these recent non-absoluteness theorems are actually interesting and important and have key things to tell us about quantum mechanics. But I don't think that the discussion of them in terms of radically relational and perspectival interpretations is really very helpful. I don't think what they show is that there is no objective reality, and I think this discussion is getting in the way of understanding what they are really saying. In particular, these experiments do seem to provide some kind of evidence for various kinds of disaccord, but those kinds of disaccord don't need to be interpreted in these metaphysically radical ways, and that way of interpreting them is arguably just getting in the way of making sense of what they would really mean. So I am not inclined to see these kinds of theorems as evidence for the non-existence of objective reality. I would like to have less focus on that way of thinking about them, and perhaps more focus on other approaches, such as relational interaction states or retrocausal approaches. So with that, thank you very much for listening. And are there any questions?
Thank you. Thank you very much. So I think that we are out of time for discussion. So, Keith.
Yeah, thanks, Emily. So, question about the disaccord 3. I don't know what the problem with it
Yes.
is. And so is the problem anything more than a pragmatic problem? Right? So the pragmatic problems are problems.
Yes.
But I see why it would be worrisome that it gives us reason to not trust our ability to, it makes it hard to trust the evidence that we have for quantum mechanics, but it's just undermining it just undermines that evidence, right? It doesn't provide us any kind of rebutting to Peter.
So I do think
it makes our picture of the world more, and our confidence in what we know about it more complicated. But is there a further problem in that?
So I think it does. It is a fatal objection because the reason we had for having this whole discussion and for believing in any of these predictions was because we thought quantum mechanics was a correct theory describing reality. And it seems to me that our belief that quantum mechanics is a correct theory describing reality depends very crucially on the assumption that we have been able to exchange information with other observers and thus gather reliable information that has allowed us to confirm this theory. So it therefore seems to me that we don't really have the option of interpreting quantum mechanics in a way that undermines the evidence that we have for believing it in the first place. So this doesn't mean that there could not be type 3 disaccord. It's not an argument against the existence of type 3 disaccord, but it is an argument against postulating the existence of type 3 disaccord as an interpretation of quantum mechanics.
Other question.
I'm just wondering how essential it was to present this argument in terms of the extended bigness friends no-go theorems. I'm wondering, was that necessary? Could you have done all of this in terms of Bell's theorem? Because you explained the extended bigness friends theorem as basically stating that, if I recall, universality of quantum mechanics is inconsistent with the conjunction of locality, no superdeterminism, and a third thing, absoluteness of observed events.
Yeah.
But you often see Bell's theorem as saying that the universality of quantum mechanics is inconsistent with the conjunction of locality, no superdeterminism, and realism. And so I just wonder, could you have sort of explained everything that you explained here, not in terms of the extended bigness friends no-go theorem, but instead in terms of Bell's theorem, where the emphasis is on the realism assumption? Oh
yeah, absolutely. I mean, the reason I'm talking about the extended bigness friends theorems here is for purely sociological reasons. It's because there's been this recent interest in them, and people have been trying to use them to push for these kinds of relational perspectival views. So my interest was on rebutting that sort of strand of thought, which is responding to these theorems in this way. But I do think that very similar conclusions already arise from a Bell's theorem case. Bell's theorem places less emphasis on the role of communication between observers. But you still do need to assume that you're able to pass information between observers for Bell's theorem, because otherwise you can't compare the correlations on either side. So even in Bell's theorem, the same kinds of issues come up. It's just a kind of presentational issue that people have not focused on the absoluteness stuff in the context of Bell's theorem, whereas they have, for some reason, been very focused on absoluteness issues with these theorems.
Does that mean that you think that the extended bigness friend no-go theorems don't teach us anything that we already didn't know from Bell's theorem?
So not quite, because the extended bigness friends theorems, the notion of locality used in the extended bigness friends theorems is slightly weaker than the notion of locality used in Bell's theorem. So it would be possible to to accept a certain kind of locality in Bell's theorems involving sort of outcome dependence, but still maintain parameter independence, whereas the kind of locality occurring in the extended Wigner's-Friends theorems involves the denial of parameter independence. And so some people are, I think, less willing to accept that.
Do you think there's any good argument based on light cones that separates outcome and parameter independence?
I personally have never found the distinction between outcome and parameter independence to be very compelling. I know other people do, and perhaps they're seeing something that I don't see. But for me, I'm not sure. I don't find that distinction very helpful.
I have another question going back to the type 3 Discord question.
Yeah.
So suppose that the way we taught students quantum mechanics is that we locked them in a building for like several years.
Yes.
And we gave them a whole suite of experiments to perform.
Yeah.
Where they would basically be able to confirm all of the predictions of quantum mechanics, including what happens at the tangled states when they observe both of the outcomes themselves.
Yeah.
So those people would then be able to come up with quantum theory, right?
So there's two problems here. One is that this depends quite crucially on the idea that you could confirm quantum mechanics on your own depends crucially on the claim that in the context of these relational interpretations, you count as the same observer over time, because in that context, you need at least to be able to trust the observations made by your past self as recorded in your memories and records and so on. And it seems at least complex to make the case that a single person remains the same observer over time in the sense relevant to these interpretations, because all of the kind of physical criteria we could come up with to track the same observer over time are somewhat approximate and emergent. And yet there seems to need to be objective, sort of definite facts about what counts as the same observer or not in these approaches. So my concern there is that you wouldn't really be able to make the case that you remain the same observer over time, and so you wouldn't be able to trust records in your memories, and then you're not going to have enough data to confirm quantum mechanics.
That's through discord between you now and you later.
Yeah, I think also there's a more general problem related to the role of this epistemic community and giving us like an understanding of what it is to be objective, what it is to be epistemically rational. I think the practice of science is very, very strongly embedded in the contributions of the whole community in terms of giving us this notion of objectivity. And I sort of struggle to imagine that it's possible for a single individual on their own to meaningfully differentiate between scientific judgments and opinions. So I think the epistemic community is necessary in that broader sense as well.
I was wondering if you could elaborate a little bit on why it's crucial to the theory of quantum mechanics that observations are absolute, or specifically this communication between a larger system and a subsystem, that the communication shared, that the two systems agree. Why is this, in your viewpoint, crucial to the theory of quantum mechanics?
So it's not crucial to the theory, but I'd say it's crucial to the means by which we have arrived at the theory. Quantum mechanics was not developed by one lone genius on their own. It was developed by the whole community of scientists. And part of that process is that different people across the world performed experiments and shared their outcomes. And it's that process of the whole community contributing, which is a big part of the confidence we have in the correctness of quantum mechanics. And as I said to Kai, certainly even if you think you don't need other observers, you certainly need to at least rely on your own memories and records in order to empirically confirm quantum mechanics. If all you have is just, the last few observations you made, and that's the only thing you can rely on, that's not enough data to empirically confirm any theory. So our reasons for believing quantum mechanics seem to be founded implicitly on the assumption that we can, most of the time, successfully share information with other observers.
Aren't the contexts here very, very different between a Wigner's-Friends or this extended Wigner's-Friends type situation and the situation in which you're describing? Because I would think that in this case, as quantum mechanics as we understand it now, all of these experiments are very much so grounded in the same, so to speak, inertial, or the same frame, the lab frame.
Mm-hmm.
With all of these Wigner's-Friends paradoxes, they very crucially rely on I think they should rely on a theory of wave collapse or something, because you're talking about a measurement, then a measurement happening outside of that measurement. And right now, as far as I understand the quantum theory, that is just incompatible with theory, right? Because the theory when a measurement happens, we're in a completely different physics. So what I don't understand the interface here between a quantum mechanical theory and communication between scientists.
So, I mean, keep in mind that there are different ways you could implement the Wigner-Friend style experiment, but the one way you can implement it is that one of the measurements just involves releasing coherent control, opening the box and going inside and asking the other observer what they observed. And the kind of the key point made that the Bong et al. Theorem makes is that if you're going to reject absoluteness of observed events, you have to say, even in that completely ordinary situation where you're just having a conversation, we still have type 3 disaccord. So if your response to the Bong et al. Theorem is to say, well, I just think that when we have conversations, we don't necessarily end up exchanging information because this is just a totally ordinary interaction. It seems like you're going to have no choice but to accept that can happen in any conversation. There doesn't seem to be any principled way to say this only happens in the Wigner-Friend scenario. It seems like you have to say the same thing can happen in any conversation we might ever have. Then that therefore undermines any method we might use to exchange information between observers.
Thank you.
Okay, so I have a question that I also had and discussed along with colleague, in particular with Kelvin, when you gave your position talk. What worried me about this idea of retrocausality is not the word retro.
Yes.
Is the word causality.
Yeah, same here. Yeah.
So what I do not understand well is what in this interpretation is called causality. Yeah. Because if the question is that there is a sort of determinism between a certain niche or a certain status at the time t and another status at the time t1, so this happens in any deterministic system.
Yes.
When you have a deterministic system, of course, you can interpret as retrocausal, because the position in the time t gives the position in any other moment of the time. So if this is a retrocausality, there is nothing strange in retrocausality, because it's not really causality in a strong sense, it's only determinism. Yeah. So I do not see what is in this interpretation, what make it clear that what we are speaking about is causality and not simply determinism. Yeah, so I actually don't think it is causality. So I'm using the word retrocausality very loosely here. I don't think there is any causation in either direction of time in fundamental physics. So I'm perfectly happy with it not being causality in a deep sense. I'm just using the word retrocausality to refer to the idea that there is some kind of dependence relation between the choice made at a later time and the outcome at the earlier time. And the existence of a dependence relation is all that we need to avoid the problem of this theorem. It doesn't have to be causal. The question is not whether the dependent relation goes in both directions or in only one direction. Yes. If it goes in both directions, you can call causality, but there's nothing to do with causality. It's only univocity. So it goes into the event 1 depends on the event 2, and also the event 2 depends on the event 1 in both directions. Yes. So I mean, direction call it causality is simply wrong. Yeah, so I mean, I'm inclined to say that in fundamental physics, all of the relations are symmetric, so they all go in both directions. But the key point here is that in this experiment, the later choice is a free choice made by an agent. So typically, the assumption that we make is that that free choice made by the agent can't be caused by this earlier measurement outcome, because it would just be too complicated to have either a sort of common cause or a direct causal relation. And so in order to allow that there's some kind of dependence between that later choice and the earlier outcome, you either have to postulate superdeterminism, which says that there is in fact some kind of really complicated joint common cause for them, or you need to say that there's some kind of backwards causal arrow. And I think on some level,
when you move to the more fundamental scales where there's no sort of well-defined direction of causation, the difference between those two approaches erodes somewhat. But from my point of view, I don't really mind whether this is referred to as causation in a strong sense or not. The key point is that you can have this dependence relation with no problems, and that will solve the problem in this theorem.
Okay. Other questions? Remark, objection, protestation?
Can you say more about why you think type 3 disaccord is a problem for doing science? Because I don't quite understand that. If my conversations with Marco depended on avoiding type 3 disaccord, we would not get anywhere. Because every word that comes out of his mouth makes absolutely no sense to me. So
yes,
and yet I think we make progress.
So the issue with
understanding each other, we make a lot of progress.
So there's this kind of utility view of language that just says that we don't need to be in accord. We just need to be close enough to being in accord to make progress.
So yeah, the issue with type 3 disaccord is not about how close to accord we are. The issue with type 3 disaccord is that there just seems to be no connection at all between what he says and what you hear. And sure, in a conversation, it's totally fine if there's some misunderstanding or some things get miscommunicated, but we still need to have a baseline assumption that, by and large, this communication process is to some extent reliable, and there's some information being transferred sometimes. The type 3 disaccord seems to be denying that any information ever gets transferred.
So that technically is part of what you think the interpretation of the theorem is, that it's not strong, that there is no connection between the...
Yeah, so there's actually an interesting variation. There have been interesting variations on this where people have looked at trade-off relations where they've allowed that there's some amount of agreement, but not total agreement. And you can kind of relax this a little bit, but you're still going to get a contradiction. That you're still going to get contradictions if you allow a sufficiently large amount of agreement, even if you allow not exact agreement.
But sorry, I did not understand very well. If I understand well, your point is that if when Alice or Chile, I don't remember which one,
yes,
the other tell this is the measure.
Yes.
No, that's not what I understood. It's not the measure. So your point is that if there is this problem on communication, we cannot base off empirical evidence to further the theory because there is no way to communicate what is the result of empirical evidence. Yeah. If this is not your point.
Yeah. If type 3 disaccord is generic, then there's just we can never rely on any report that anybody else gives us. We can't even think it's like maybe a little bit reliable. We just have no reason to think there's any correlation with reality at all.
Okay, but the problem is that when you tell me the problem, I don't know what is the problem. So what I see, if you tell me the measure is 95.
Yes.
And I say, no, it's not 95. One thing is I say it's not 95. And if any other thing than 95. But another thing I say is not 95, is 3 or 94. Because if I say it's not 95 or 3, we still way to agree on the fact that it's either 95 or 3.
Yes.
And so we have some information for empirical evidence.
Yeah.
And if the argument is it's not 95, but it is 94, so now we are close to what Drew says. So the problem is to understand what does it mean and not agree.
Yeah, so what it's
very general.
So I mean, specifically what it means, what it seems to mean here is that there's just no correlation between what he says and what you hear. So he might as well not bother speaking to you at all. You might as well just guess. That would be exactly as successful.
So there is no way to take any information for what he says.
Yes. That's the problem. Yeah.
Well, that's true. So
that's it. But of course.
I wanted to ask, because right now it sounds like a lot of this relies on, for example, laboratory experimental data being absolute, and the theory of quantum mechanics relying on this. But historically, and the way that modern physics is thought of, that's not the case. Laboratory observations are not considered absolute.
What do you mean by absolute?
They are reliant on your frame of reference. All quantities in physics are relative.
Yes.
And they're relying on your frame of reference. And the whole idea between gauge field theories is getting to like the actual underlying physics.
Yeah.
And this is an agreement with quantum mechanics and multiple observers.
Yeah.
But these are the underlying things.
Certainly, yeah.
Yeah. So, for example, if we go to relativistic physics, there's the famous example of a school bus running at relative speed into a barn, right? And a person in the school bus will say, I don't remember which one is which, but the person in the school bus, let's say, will say that the bus does not fit in the barn.
Yeah.
But the person outside the school bus says the bus does fit outside the barn. And then when they communicate, this would be a type 2 disagreement, right? According to you. Where the person outside of the bus sees something that does not agree with the person inside of the bus.
Sure, yeah.
But the person inside of the bus can also relate the coordinates of the event of the front of the bus going to the doors and the back of the bus going to the doors in invariant space-time intervals.
Great, yeah, exactly, yeah.
This is generally how I would think of a interaction between somebody inside of the box or outside of the box.
Right.
The relative physical data that is relayed would be data that can be appropriately transformed.
Yes.
And I'm just asking if, am I talking about something different here?
Yes, you are. So I'm glad you brought this up though, because this is an argument that proponents of relational and perspectival views sometimes make. They sometimes say, well, making things relative was useful in relativity. Let's just do it in quantum mechanics too. And in fact, I have no objection at all to making certain kinds of facts relative in quantum mechanics. I think that is the right thing to do. But what these relational and perspectival views want to do is something a bit stronger than what happens in relativity. So in relativity, certain kinds of facts are now regarded as being relative to a context or frame of reference. But there is, as you say, still this background invariant. There are still absolute facts in the background which ground the relative facts and explain the relations between them. And what these relational and perspectival approaches want to do is deny the existence of any such third person absolute view at all. They want to say there are no absolute facts at all. There are only relative facts. And therefore, if there are no absolute facts at all, that means we're not going to be able to exchange any information between perspectives because there's no sort of absolute background against which we could do that. So what they're doing is something much, much stronger and more radical than what's happening in relativity. The lesson I take from relativity is not that it's good to relativize things, but the real content of a theory is what's invariant, what's left behind. And so it doesn't make sense to me to look at quantum mechanics and say there's nothing invariant, there's nothing left behind, because then there's just no theory.
Okay, right. So to take this a little bit further, because I have one more. Do you have an example of such a measurement that would lead to a true type 3 disaccord? Because I am just, as someone who works with experimental data and I've seen similar disaccord between subsystems and whole systems arise in experimental settings. It all comes down to a coordinate transform.
Yes.
Right. And I am having trouble imagining a scenario that I can visualize where such a thing would happen. Are you working on it, or is this like far away in the theory?
Well, I mean, you can postulate type 3 disaccord in any interaction you like. I could choose to postulate that the conversation you and I are having right now involves type 3 disaccord, and that what you hear is not the same as what I hear. Kind of by definition, it's not going to be possible for me to establish what you are hearing instead, because I can't communicate with you. But in any interaction, one could imagine that it involves type 3 disaccord. I don't think that's a good route for science to go down, but it's certainly it's a possibility. I wouldn't be inclined to spend a lot of time building theories involving type 3 disaccord just because I think this is not a useful route to go down. But you could, if you wanted to, try to formalize what the dynamics of such a theory would look like. They would be pretty weird dynamics. They would be sort of, the systems would interact, but in some sense never become correlated with each other. So it would look like an odd kind of theory. But yeah, as I say, I'm not inclined to sort of go and make that more explicit because I'm not sure that's a useful scientific route.
Well, I thought of lines. I don't know if I got what I was trying to say across.
Oh, sure.
Just a kind of thought to maybe try to bring out how weird this would be.
Yes.
So suppose that, because we're talking about just complete unreliability of information.
Yeah.
There's a lot of information that we can share and then we can sort of independently verify.
Yeah.
And so in our own experience, we'll verify. It may be that we each have completely independent experiences and somehow they seem to verify the things.
Yeah.
So the example I was thinking of is that I give you my phone number. I know what number I thought I gave you, but you got a different one. And then you call me using the different one, but somehow it works. And I'm the one who answers the phone.
Exactly. Yeah.
Maybe maybe it's not even me who answers the phone because we can't communicate in the first place.
I just get some kind of mirage of you that answers the phone. Yeah.
So when you really try to take this seriously, a lot of our very fundamental notions about how reality is just fall apart completely.
Right.
So the problem is actually worse than just giving up empirical science.
And I think, I think there are, quantum mechanics does force us to give up some assumptions about reality. And I think there are some that we can give up. I think locality, for example, can be given up without disastrous consequences. But whereas I think the fact that we can communicate with each other is not something we can reasonably give up as an interpretation of a scientific theory.
Are you familiar with the paper that Matt Leifer and David Schmid recently wrote? Okay, so a few weeks ago, this group listened to Matt Leifer give a talk on these extended bigness friend no-go theorem, and there was a bit of a technical issue where he didn't bring his laptop cord and it crashed, and as a consequence, I don't know about others, but I didn't entirely follow everything.
Yeah.
But
sorry, Matt is not here, but he asked to record the talk.
That's fine. An additional lesson to bring your cord. But really, my question was to try and relate these two talks that we've just seen. And from what I understood from Matt Leifer's talk, it sounded like he maybe not I don't know if he'd describe it as a type 3, but it was seemed like a perspectival. He was looking for what he was calling a neo-Copenhagenish route.
Yes.
Which sounded like a perspectival, which sounded like it might fall under your criticism, but I'm not sure. I was wondering if you could maybe try to connect the talks.
So the neo-perspectival approach that Matt likes, as I understand it, falls under the general class of what I call orthodox interpretations. And all of the orthodox interpretations, as I understand them, have this general problem that if you follow their postulates to their logical conclusions, it seems that communication between observers is impossible. So I think this concern about intersubjectivity certainly applies to the neo-Copenhagen views and to various related views like some versions of relational quantum mechanics, possibly some versions of cubism and so on. There's this whole class of approaches which have in common the denial of any kind of objective third-person view. And it seems to me that if you deny the existence of an objective third-person view, the failure of communication follows sort of immediately from that.
Interesting. Okay. Yeah. So the neo-Copenhagenist view sort of undermines the kind of intersubjectivity needed for agreement.
Yes.
Ground science.
Yeah, that's my understanding. Yeah.
Other questions? Hi.
Sort of a tangent question. It goes back to the conversation you two were having about retrocausality and causality specifically. So if you think that there is determinism between two things, but there's not any kind of direction between it, how do you make sense of one of them being free? I'm just like, I know I kind of see how you might do it, or if like so even if you're talking about like an all-at-once theory, when does the free choice fit in there? Because if they are related in some determined way, that this choice up here determines something in the past, but it can't be the other way. So that can't be a symmetric relation, right?
Well, I think of the symmetric relations as applying primarily at the level of fundamental physics, whereas I think of freedom as a concept that's best applied at macroscopic scales. And at that point, we're going to be appealing to things like thermodynamic asymmetries to understand what consciousness is and what it would mean for a consciousness to have freedom. So I just think of those as being kind of incommensurate. They just apply at different sort of levels of analysis.
So in the higher level, there would be something like a free choice, but at a deeper level, it would have all been pinned down.
Yeah, I mean, I have a broadly compatibilist view when I don't think you need to, yeah.
Other questions? If not, thank you very much.
Thank you.
Good vacation, and then we meet again. Happy Christmas, Happy New Year, and we meet again in the room on.